Okay, we'll go ahead and get started. Quite a bit to cover today. So our topic today is generalized linear models. And last month we talked about linear models, the general linear model, but the topic today is generalized linear models. And so if you remember from our discussion last month that for linear models, our outcome variable was a continuous variable that was more or less normally distributed. So in generalized linear models, the most often, or the most ones that most people are familiar with, or that's actually most used in literature, is logistic regression, where we have a binary outcome. Yes, no, positive, negative, good, bad. But we also can do ordered logistic regression, where we have more than two outcomes, but they are ordered. So example of this would be like disease stage or cancer stage. And then we can do what's called multinomial linear regression, where our categories are unordered. And I'll give examples of both of these later on. And then the last method that we want to talk about is Poisson regression, and negative binomial regression. And so in this case, what our outcome data is counts. And so for example, maybe we want to look at the number of ICU infections per month, or something that is a count. So in linear regression, as I mentioned, we have a dependent variable, whereas it's continuous, and then our regression coefficients, the B's or the betas, are changed, or a change in the outcome for every unit change in the independent variable. And we looked at R squared as the proportion of variance in Y accounted for by the independent variable or variables. So in logistic regression, as I mentioned, our outcome is dichotomous. And so this is in doing the analysis in any statistical software. Typically, you code the outcome that you're particularly interested in as 1, and the other outcome is 0. The odds of the outcome is defined as the probability of the outcome divided by 1 minus the probability of the outcome. And so we can model this in our usual regression way, where we have the log of the odds as a function of a regression kind of equation, where the regression coefficients, the betas in this case, and x is the independent variables. And we refer to this, the log of the odds, as the logit. And we interpret this similarly as we do in linear regression, where we have a change in the log odds of the event with a 1 unit change in the independent variable. And it can be increasing or decreasing. And so as we looked at, or maybe we didn't, I don't remember, but I'm sure everyone's familiar with the normal distribution and what that looks like. You have a symmetrical distribution. Well, this is what the logistic distribution looks like. And you notice that in kind of the middle of the distribution here, this is pretty linear. But if we go out to the tails of the distribution, you can see that it's not linear. And as we'll see, if you have an outcome that happens almost all the time, and we're in this part of the curve, then we're probably going to run into some issues. And then the same thing with a rare outcome, or it doesn't occur very often. So in the tails of the distribution, we're probably going to have some issues that we'll need to look at. So as I mentioned, the slope coefficient from the logistic regression is the rate of change in the log odds of the event as the independent variable changes 1 unit. And given the regression equation, then we can calculate the probability of the event as a function of the independent variable. And so the probability of the event is just the exponentiated regression equation divided by 1 plus the exponentiated regression equation. And so we can calculate the probability of the event given any particular value of the independent variables. So and the beta coefficient, the regression coefficient, will have a sign, positive or negative. So if it's greater than 0, then there's an increase in the log odds for every 1 unit increase in the independent variable. If the regression coefficient is negative, then that means there's a decrease in the log odds. And if it's the coefficient is 0, that is statistically 0, then we don't have any relationship between the log odds and the independent variables. And in logistic regression, if you exponentiate the regression coefficients, you get the familiar odds ratio. And so we'll see how that works out in some examples here. So here I have some data that I created that looks at coronary disease as a function of age. And so our coronary disease is coded as 1 or 0, 1 if they have coronary disease, 0 if the patient doesn't. And then the age is recorded as a continuous variable. And so this is the output of our regression equation. This is in Stata, but it'll look the same in most every statistical software, whatever you use. So we have the regression coefficient for age is 0.097, the constant minus 5.16. And you can see that in this case, the p-value tells us that it's statistically significant. The 95% confidence interval does not include 0, which if it's statistically significant, that would be the case. If the confidence interval includes 0, then it's not going to be statistically significant. And so at the bottom here, we can calculate the probability of cardiovascular disease at any particular age. So we have the exponentiated regression equation and the whatever the patient's age is times the age regression coefficient, and that's divided by 1 plus the exponentiated regression equation. So we can also exponentiate the regression coefficients. And so if we do that for age, we get an odds ratio of 1.1. And now our confidence interval will, if it's statistically significant, not include 1. If it includes 1, then it won't be statistically significant. But you see, we get the same p-values as we did with just the regular regression coefficients. And so how do we interpret this? The odds ratio. So for every 1 year increase in age, the odds of cardiovascular disease increases by a factor of 1.1. Or another way of saying that, saying the same thing, that for every 1 year increase in age, the odds of cardiovascular disease increases by 10%, or just the odds ratio minus 1. We can calculate an odds ratio from a 2x2 table of events by, in this case, independent groups. So here we have an intervention and control group and the number of events and the number of not events. And so we can calculate the odds ratio by taking the probabilities here. And obviously I made the numbers, so this would be easy to compute, but it's the intervention, the proportion of the events divided by 1 minus the proportion of events, and then that's divided by the same quantity with a control group. So in a 2x2 table, this is actually, we can simplify this. And so we can calculate the odds ratio just by taking the ratio of the diagonal elements. So for the intervention, it's 46 times 63 divided by 37 times 54, and we get the same odds ratio, 1.45. And so what this means, we would, at the odds of event, are nearly 1.5 times more likely in the intervention group. And whether this is statistically significant or not, we can get from just doing a chi-square for the 2x2 table. And statistical significance for an odds ratio means that it's different from 1. We can then do, obviously, multivariable logistic regression, just like we could do multivariable linear regression. And of course, what this means is that we have more than one independent variable. And the independent variables can be any type, dichotomous, ordinal, etc. And so it's the same sort of thing. We're modeling the log of the odds with the regression equation. And so just as are similar to the interpretation in linear regression, the regression coefficients here are adjusted for all other regression variable or all other independent variables in the model. So, for example, beta 1 is adjusted for x2, x3, and so on. But it has the same interpretation, except in terms of a increase in log odds for 1 unit increase in the independent variables. So here's an example where our study was of 30-day readmissions. So the outcome here is readmission within 30 days, yes or no. And so we have a number of variables here that we're looking at in our model. So for example, age, which I have 10 years there, that means that we have looked at age in 10-year increments rather than just 1-year increments. And so our odds ratio is 1.25, which is statistically significant. So what that means is that the odds of being readmitted within 30 days increases by 25% with every 10-year increase in age. And then the same interpretation for female, and this odds ratio is in relationship to obviously males. So this means that females, that the odds of 30-day readmission are 18% greater in females than they are in males. And then we have race, which now has 3 categories. So whenever you have a categorical independent variable, one of them is what we call the reference group. And so in this case, I've made whites the reference group. And so you see you just put in their odds ratio as 1. And so when we have this odds ratio of 1.3 for blacks, what that means is that blacks are, that the odds of readmission is 30% greater in black race than it is in white. And so this is also statistically significant. The odds or the confidence interval does not include 1. And then for the other race, again, this is in comparison to whites, there's no difference. The odds ratio is almost 1. Now we can also do a test for whether blacks are different from other races, which it probably is, but I haven't done that here. And then we have a number of dichotomous variables, whether their procedure was elective, whether they were transferred from another hospital, whether they had a previous hospitalization. The Lexhauser count is a continuous variable that gives an index of the comorbidities a patient might have. So in this case, the odds ratio of 1.21 means that for every increase in the number of comorbidities, the odds of being readmitted increases by 20%. And then congestive heart failure and renal failure are again yes or no outcome or independent variables. So the interpretation of their of the odds ratio is the same as we have indicated for females and the other dichotomous independent variables. Okay, and at the bottom you see that I have something called a C-index, and it's 0.76, and then the confidence interval for that C-index. And so what is a C-index? Well, there are two measures that we want to look at when we evaluate logistic regression models, and that's discrimination and calibration. And discrimination means that our model, however many variables we have in it, is good or not good at discriminating between those who experience the event and those that don't. The C-index numerically turns out to be the same as an area under a receiver operating characteristic curve. And it varies, well, from 0.5 to 1. 0.5 meaning there's no discrimination. In other words, it's a toss-up whether a patient experienced the event or not. If we have an index that's 0.8 or better, then we've got really, really good discrimination. And this is kind of a matter of, I guess, interpretation, but in my view, if you get a C-index of 0.6 to 0.7 there, it's kind of mediocre. Although I have seen articles where they call a C-index of 0.6 something really good, which I don't think is the case. But anyway, the other index that we want to look at is what we call calibration. And what this is testing is whether the predicted probabilities from our model equal the observed probabilities in the data. And so the way that this is usually looked at is that we make a plot of the observed probabilities with the predicted probabilities. And if they're the same, then we're going to get a slope of 1 because they'll have a 1-to-1 correspondence. Now, obviously, we usually don't get a perfect relationship here, but this is usually presented sometimes in a bar graph like this. So this is a calibration plot for our 30-day readmission model. So you can see it's pretty good. As the observed proportion readmitted is pretty consistent with the predicted readmission. That is, as one is increasing, so is the other. Obviously, it's not perfect. But the other way of presenting calibration is to actually do a plot of the lines and look at the slopes. And so in here, the red dotted line is the perfect, would be the perfect calibration. In other words, we'd have a slope of 1. And from our data or our model that we did this, our calibration slope is 0.97. So that's really pretty good. It's pretty close to 1. And so here's an example of how this is presented in a journal. And so I want to kind of go through this a little bit to just illustrate some of the good things and some of the not so good things in the literature. And so this is a study that looks at repair of mitral regurgitation versus medical therapy. And so it's a randomized trial. They had severe mitral regurgitation, and then it was either mitral valve repair plus medical therapy as our treatment group, and they're comparing it to medical therapy alone. So they had a good number of patients. They recruited patients from 37 different institutions, and this was done in France. So in their statistical analysis here, they start out with their power analysis, or they're going to see how many patients they need to randomize. And so to do this, they're taking previously published literature where the outcome, and they're defining the outcome here as a composite of death from any cause or an unplanned hospitalization for heart failure at 12 months. So they found in previous literature that it could be as high as 50%. There's a previous study that they found that had a rate of 33%. So they powered their study on a 17% difference between mitral valve repair and medical therapy. And they did this just using a straight chi-square test, and then they adjusted their number to allow for a 10% loss to follow up. And the outcome was modeled with unconditional logistic regression. And what we mean by unconditional is that there's no other variables included in the model, like age, sex, or whatever. And of course, the reason that they're doing that, they can do that, is because it's a randomized trial, that whatever other potential variables might influence the outcome have been more or less equalized between the two groups. And so what they found in terms of their primary outcome, death or hospitalization for heart failure. And so in this case, obviously the outcome is dichotomous. So you can have either death or hospitalization or both, but to obviously not have the outcome, you have to have neither died nor been hospitalized. And they had some other variables they look at, but they said they didn't really analyze those because of missing data. But anyway, what I want to focus on is their findings that 83% in the mitral valve repair group had the outcome, but in the medical therapy group, 78 or 51% did not, or 51% had an event. And so this turns out to be an odd ratio of 1.16, which is not statistically significant. But if you think about how they would have done this, so they would have coded their outcome, death or hospitalization, as a 1, and no outcome as a 0. So if you look at this, you see, and you can see by the percentage here, that the repair group is actually doing worse than the medical therapy group. And so if you look at the odds ratio, that means that the mitral valve repair group, the odds of the outcome were 16% greater in that group than they were in the medical therapy group. So they didn't really get the outcome, I think, that they were looking for, and it wasn't statistically significant anyway. And so here's how they present their results in a table here, the composite outcome, and then usually you see this if you have a composite outcome, they break it up into the different individual outcomes, which is not really the thing that you want to do, but they kind of recognize that, and so they don't put any p-values though there, although they would all be non-significant, because you can see that the confidence intervals include 1 for their secondary outcomes. And then in addition, they also do a Kaplan-Meier survival curves for the two groups, and you can see that there's very little difference between the two. And so here, rather than looking at the outcome as happening within a 12-month period, yes or no, they look at the actual time and then plot that in the 12-month period. We'll look at survival, how you do time to event analysis next month. So in their conclusions then, what we find is that they didn't have power because they found no difference, and the odds ratio of 1.16 didn't suggest a trend in favor of microvalve repair anyway. And so they conclude at 12 months there was no difference between the intervention and control group. Well, that's not quite the way you say that, because you don't really know whether it's different significantly because you don't have the power. But the way that you would state that is at 12 months, there was no evidence of a difference between microvalve repair and medical therapy. So just kind of fine points there in how you present non-significant results. And then, so another issue that you might encounter in logistic regression is extreme values. And so I've looked at a model here, which I think, again, is doing readmission, 30-day readmissions. But anyway, there's some other variables in here. But you notice I've highlighted some that are either really small or really huge. And so, for example, in intervention year 2, the odds ratio is 0.01. And you see that the lower bound of the 95% confidence interval is getting close to 0. So when you see something like that, and the same is true with the other race, with Medicaid compared to private insurance and self-pay, you see that the odds ratios are virtually 0, as are the confidence intervals. So this, even though statistically that's significant, that tells you that there's some issue going on there, probably that there's very few patients with Medicaid or self-pay or other, that maybe we would have been better just grouping private insurance with anything else. The other one, though, is for females. You see that the odds ratio is really quite large, and the confidence interval is really, really wide, from 1.8 to 292. So whenever you see something like this, where you get really extremely small values for the odds ratios and confidence intervals, or really huge values, there's some issues there that you need to look at as far as interpretation. Some other issues that that you can think about when doing logistic regression is that you will often see, and I'm going to give you an example, where we're going to categorize continuous variable. Now that can aid in interpretation, but whenever you do that, actually regardless with any analysis, whether it's logistic regression or linear regression, you're going to decrease the power that you have in your study. And if the relationship between the outcome and continuous variables is nonlinear, then the interpretation of the odds ratio won't be correct. And then finally, model discrimination. And calibration really matter. So even if you get a model that is statistically significant, but the C index is less than, well, you can argue about this, but if it's, around 0.5 something or 0.6 something, then I think you need to look at your model as not being very good. Okay, so then we can do logistic regression if we have more than 2 categories. And as I mentioned, these are ordinal logistic regression, where we have ordered categories or unordered categories, multinomial logistic regression. And so here's an example of unordered or multinomial logistic regression, where we have our outcome is morphology in hypertrophic cardiomyopathy patients. And so we have 3 categories here: basal septal, reverse curvature, and then the others are lumped together, which you see as a much smaller number than the other 2. And so what we're going to do is we're going to analyze morphology as a function of age, sex, and BMI. And so this is our results. And so you can see again, because we have different categories here, we're going, or 3 different categories here. In this case, we're going to have to use one as the base outcome. So when we look at the regression coefficients, and so, for example, we see 2 that are statistically significant for the reverse curvature, age and BMI. That is interpreted in relationship to basal septal. So in other words, if we exponentiate age, for example, or BMI, we get an odds ratio of about 0.97. And so that's in relationship to the basal outcome. And so the way that we would interpret that is that for every year increase in age, for example, the odds of reverse curvature are reduced by 3% compared to basal septal. And that comes from now, because the odds ratio is less than 1, to get that percent, we're just going to take 1 minus the odds ratio to get the percent. And then for every unit increase in BMI, we get basically the same result, that the odds of reverse curvature are reduced by 3% compared to basal septal. The other category, none of them are statistically significant. So that means that we don't have much of a difference between the other groups in basal septal morphology as far as age and BMI and male are concerned. So now let me give you an example of an ordered logistic regression, newborn weight categories by inflammatory markers. And so now we're looking at weight in grams as a function of these inflammatory markers, and we have 3 here: IL-4, 6, and 8. And we could have looked at weight as a continuous variable, which it is. However, often in newborn research, they like to put these in categories because the risk of infant mortality or other comorbidities that might happen increases with smaller birth weight. And so you often see this in their literature. But be that as it may, we have categories of less than 750 to 1,000, and then greater than 1,000 grams. And in this case, you see that the comparison group, we've made the greater than 1,000 grams. And so nothing is really significant as far as less than 750, but in the 750 to 1,000, we have some that are statistically significant. In particular, IL-6 and IL-8. And so, again, our odds ratios are very small. So what we often do in a case like this, and we could have done it in our other one that we looked at, is we can look at, in this case, the inflammatory markers in more than one unit. And so what we do is we take the regression coefficient, multiply it by whatever factor we want to talk about or look at. So in this case, I use 50. I think PG is picograms per milliliter anyway. So we multiply the regression coefficient by that value, and then we take the odds ratio of that. And so if we do that for IL-6, we get a odds ratio that is less than 1, 0.45. And so what this means is that for every 50 unit increase in IL-6, the odds of infant weight comparison to the 1,000 gram are reduced by 55%. And for every increase, 50 unit increase in IL-8, the odds of infant weight are increased by 6%. Again, in comparison to the 1,000 gram group. So this is often done like like, for example, BMI is a continuous variable, but often that's categorized into underweight, normal weight, overweight, and obese, or maybe there's a couple of categories of obese, because that's usually the way it's talked about in their literature. So we might look at, if our outcome is BMI, look at that as a categorical variable as well. Okay, so we've talked about continuous variables, ordinal variables, categorical variables. And as we saw in one, they did a time to event analysis. So we're going to look at that next month, looking at time to event analyses. The other one that comes under the, or another one that comes under the count of generalized linear models is analyzing counts. In other words, you just, count how many events there were. And usually this is within some exposure time. Often that's assumed to be the same for all patients, although it's not necessarily the case. And so an example might be infections in a particular length of hospital stay, or infections in the ICU over per month, over a 6-month period, or 1-year period, or something like that. But we're just counting the events. So to do this, we're going to use the Poisson regression or the Poisson distribution. And so the idea here is that the events that we're talking about obviously could occur more than once in a patient. So maybe a patient has, obviously, maybe they have more than one infection over the course of their stay in the ICU or in the hospital, or maybe they don't have any. And so in this case, we might have an issue with rare events, like we did with the logistic regression, when the probabilities are either really large for the occurrence of an event or really small. And as I mentioned, then these look at the Poisson distribution within some exposure of time. And so the Poisson distribution is defined by its mean and variance. And if you remember about the normal distribution, is defined by your mean and standard deviation. Here it's defined by the mean and variance, And if we have a true Poisson distribution, then the mean equals variance, and we call that equidispersion. However, in medical data, often it's not equidispersed, and so often it's right skewed. And, however, as the counts increase, that is, then the Poisson distribution tends to be normally distributed. So if the counts get large, we usually analyze it as continuous. So heart rate is a good example of this. Obviously, heart rate is a count, but because it's so large, that is, you don't have heart rates around 0 or 10 or 20. We analyze heart rate as continuous. And this is just an example of distributions for the Poisson distribution, and the lambda here is the counts. And so you can see as the counts get large, when we get to 10, 10, you can see that looks pretty normal. Whereas if it's small, if the counts are small, then it's a skewed distribution. So, so often, particularly in medical data, the variance is greater than the mean. In other words, what that would mean is we have a lot of zeros. And if this is the case, then we say that the Poisson distribution is over dispersed. And if that's the case, then we use a different statistical analysis called negative binomial regression. And basically what this does is that there's a parameter added to the regression equation that adjusts for over dispersion. I'll give an example of that. Okay, so here our study is looking at cardiovascular events in hypertensive patients. And so our hypertension is defined by stages, and that's defined by blood pressure values. So stage 1, which is 140 over 90, which would be considered more or less normal, although I think 130 now might be the cutoff. But anyway, stage 2 is 160 over 100, and then the most hypertensive is 180 over 110. So in this study, we had 6,600 patients and over 1,200 events. And so in terms of data that we have nearly 25,000 patient years to analyze. And so what we're going to do, well, first of all, here's what the data looks like. So we have our hypertension stage, then we have our blood pressures, gender, race, age. The years here is their years of follow-up. So that's what we're going to use for our exposure time. And then what we're going to look at are different cardiovascular outcomes. I'm just going to focus on stroke, chest pain, and then acute myocardial infarction. And so that's going to be the counts for any one individual patient that they've had in their exposure time or their follow-up time. So here's our model. We're going to model stroke as a function of stage 2, stage 3. And of course, in this one, stage 1 is the reference group by age, by sex, male being our reference group, and then white and black. And in this case, the other race category will be our reference category. And so we have what we call dummy coded our dichotomous independent variables, stage 2, 3, and so on. Age is continuous. And then our exposure is going to be years from their index visit to about midway through 2006. And I put question marks there because it wasn't quite sure that's when it ended for everybody. But anyway, so here's our regression output, our results. And so you can see that for each stage, or for stage 2 and 3, that's a comparison to stage 1. And so obviously stage 3, we can see that you would think we're going to have more strokes than patients in stage 1. Then we have female, white, black, and then age. And so again, these are the regression coefficients that we have listed here. And what we're going to do then is we're going to exponentiate the regression coefficients to get what we call an incident rate ratio. And so this is just another way of presenting the data here. And so here are exponentiated regression coefficients. And so the interpretation here is that, so for example, for age, then the expected number of strokes increases by a factor of 1.03 for every year increase in age. And if we say look at stage 2, where it's 0.94, that's less than 1. So it decreases by a factor of 0.94 in stage 2, or by 6%. And for stage 3, you can see that the incident ratio, they're about 2.2 times more likely to have a stroke than patients in stage 1. Now you might say, well, what about comparing stage 2 and 3, or whites versus black? Well, we can do that. I won't go through actually the computations because usually in the statistical software, it provides a way of doing that. And so here you see that I've done a test comparing stage 2 with stage 3. Obviously, there's a significant difference there. And the same thing for white versus black, that there's a statistically significant difference between the two races. So it turns out that in our data here that our outcome stroke is over dispersed. In other words, we can see this quite readily here, that the mean is 0.036, the standard deviation is 0.21. Well, you just take the square of the standard, you square the standard deviation to get the variance, and so you can see that we have a distribution here that's in terms of Poisson distributed is really over dispersed. So we're going to use the negative binomial regression to correct for this over dispersion. And so here's our results. You can see that they actually are kind of similar to the other results in terms of what's significant and what's not. But at the bottom here, we have this log of alpha and then the log of alpha. And this is our alpha is our correction for over dispersion. And then it does a test of whether we need to account for this or not. It's a test. If alpha is 0, then we can assume it's Poisson distributed. But in this case, it's highly significant. So that means that we really do need to take into account the over dispersion. And we can do the same sort of thing that we did with the regular Poisson regression. We can test differences between, like, for example, stage 2 and 3 and whites versus blacks. And again, they're statistically significant differences. And so again, here's the exponentiated regression coefficients. And so in our Poisson or our negative binomial regression, these are what we call incident rate ratios. And so again, stage 3 has about, the incident rate ratio is about 2.3 times that of stage 1, and so on. You see that they're fairly similar to the when we did the regular regression or Poisson regression. What else we can do, and we can do this either with, if we use Poisson regression or negative binomial regression, we can get a probability of the counts or an estimate of the counts. And so here, what I have for each stage, for the hypertension stage 1, stage 2, and stage 3, as the mean strokes, the mean stroke rate, and then the mean exposure time or follow-up times for each hypertension stage. And so what we want to do is calculate then, what we can do is calculate predicted rates from our model, and we can do this for however many patient years we want to do. In this case, I've done for 1,000 patient years, and these would be adjusted for age, gender, and race. And so for stage 1, we take our mean rate and divide that by 1,000 patient, or our follow-up time by 1,000. So what that means is that for stage 1, we have 5.7 strokes per 1,000 patient years. For stage 2, 6.3 strokes per 1,000 patient years. And then you can see why stage 3 was significantly different from both stage 1 and stage 2, that we have nearly 8 or 17.5 strokes per 1,000 patient years. And so in this case, analyzing count data, then we can get an incident rate for our different groups that we want to compare. In this case, it was hypertension stage, but maybe you might have intervention groups, and so we can do the same sort of thing for that. Okay, so I want to just mention a couple other analyses that we can do related to counts. And so we can do what's called a zero-inflated Poisson regression. And this means that we have excessive zeros. In other words, the event didn't happen in most of the patients. And so there's a way of doing that. And I think in most statistical software, there's probably a programmer routine for zero-inflated counts. And then the other one that I'll mention, maybe later on, I'll give an example in another session, but those are what we call hurdle models. And so in this case, we actually do 2 analyses. The first one is actually a binomial test. And so we test for whether there's evidence of counts that are greater than 0. So here our outcome is going to be 1 if they have counts greater than 0, and it's going to be 0 if they don't. So we do that test to see if that's the case. And if it is, if we get a significant result or model, then we can do an analysis that estimates the counts greater than 0. And so it's like in this case, we're assuming that they have some sort of count greater than 0, and so we're going to do an analysis that estimates those counts. So it's like we're excluding the 0 now in this second analysis. The thing about this one, though, is that it can be kind of complicated because we might get one model, we might get a model for the evidence of counts greater than 0, and maybe a different, maybe even a slightly different, or maybe a largely different model when we actually estimate the counts. But that's okay, because we're doing basically a two-step analysis here. But these are different analyses in handling or for special cases of counts. Okay, I will stop there. And if we have a couple minutes left here in the hour, if you'd like to ask any questions, I think we use the Q&A for that. Or if you just want to email me questions on my MedStar email account here, you can do that as well. And I might mention too that this presentation is recorded, and the Georgetown folks put that out on YouTube, I think, and I believe they send that out to everyone that is registered for the session. Okay, so if there are no other questions, then I want to thank you for your time. And next month, we will look at time to event analyses, or survival analysis, it's called in medicine, or failure time analysis if you're in manufacturing. Okay, thank you for your time and attention, and we will see you next month, I'm sorry.